Good morning. So you are in the signals and arterial performance measures session. We have 4 presentations, and so what we want to do is the presenter will spend time presenting, then we're going to leave a few minutes after each presentation for Q&As, and then at the end of the 4 presentation, we have a little bit more time for overall Q&As. So let me introduce our first presenter. His name is, oh good, we reflected the change. So this is slide changes from your printed program. David Flessner is an undergraduate mechanical engineering student at Ohio State. He has been working at the Automated Driving Lab and OSU for the past year, working on this visualization tool that he will be sharing with us today. So his presentation title will be on intersection data visualization tool for V2X application deployment. So David?
I'm David, and with my lab, we developed this vehicle to infrastructure tool for V2X application. So a brief overview of V2X communication. We talked about it a little bit yesterday, but it's really vehicle to everything communication that can be implemented with a lot of different technologies, and it enables a lot of different applications. And this is really where a lot of the advantages of automated driving comes from. So vehicles can communicate with other vehicles, homes, the cloud, other networks, pedestrians, and also infrastructure. So my tool primarily focuses on vehicle to infrastructure communication, and with that, it communicates with traffic lights, and a traffic light is also represented here for that. But it doesn't have to be traffic lights. It can be other intersections with stop signs or roundabouts, or just not intersections at all. For an example, over in Ohio by Columbus, ODOT and local governments have spent about $4.8 million lining US 33 with fiber optic cable to enable this vehicle connectivity. And so they've routed about 80 miles of fiber optic cable down this highway right through the center of Ohio. So some of the benefits, so about 40% of crashes in the US are intersection related, and of those, about 44.1% are attributed to inadequate surveillance of the driver. So this is a really significant percent, about 18% total, where if we have better communication and better surveillance of the area, we can really cut down on many of these collisions. So how this actually works is that we can have improved detection systems with traffic lights and warnings to be issued to drivers to make sure that they understand everything that's going on at the intersection. And some of the communication some of the information that's communicated is traffic light phase and timing to improve fuel economy, and also information about surrounding vehicles or vulnerable road users to help just give better awareness at intersections. So an example of this is in Marysville, Ohio. They've started implementing smart intersections or traffic lights with cameras on them to observe the lanes. And so what they can do with this is if they see, for example, a car about to run the red light, they can take that information and send it to cars in the crossflow and saying, hey, there's a car about to run this red light, you should probably stop. So how is it actually implemented? So there's many different technologies for this. DSRC, wave, cellular communication, Bluetooth, or Wi-Fi are really the main ones right now. The project I developed focuses on DSRC communication. So this is where the federal government has designated a set bandwidth for connected vehicle communication over DSRC. And this is a little schematic right here kind of showing how it works between infrastructure and vehicles. And so some of the data that's communicated with this is intersection geometry. So a lot of map data, a lot of things like reference point in latitude and longitude and relative positions off of those reference points, in addition to lane width and other physical parameter or other physical entities such as crosswalks, bike lanes, sidewalks, medians, or really any other things like road barriers and such. In addition to signal timing, so time to next phase and current phase state of the traffic light. And so this tool that we made focuses primarily on that map data, and it integrates it with a Google Maps API to plot the central reference point and the relative points over top a satellite image of the intersection. So this works with any data passed with the same communication protocol. So this is the DSRC IEEE protocol. So if the data uses that protocol, my tool can be used at any intersection and anywhere in the US. One main limitation of this is that unfortunately the relative nodes the data is given in centimeters, but the Google Maps API only accepts latitude and longitude, and mainly anything you're trying to plot on a kind of global level needs to be in latitude and longitude. And there's not really a perfect conversion between those. So over shorter distances, it stays relatively accurate with some rough conversions, but lots of error starts to accumulate over longer distances, over a kilometer or two. So this is just kind of a basic graph, just showing some of the relative points that we're plotting, and it looks like an intersection, which is great, but this is a little more interesting of a plot. So this is an intersection in Dublin, Ohio, just showing the lane nodes that the traffic light communicates to the vehicle. There's some kind of random ones, I'm not really sure where those come from, but for the most part, you can see the nodes going up and down, east and west, from north and south, east and west from the intersection. So if we zoom in a little bit to the right side or the east side of the intersection, you can see that it plots well over this intersection right here. The nodes are relatively centered in the lanes, and it can also account for these short turning lanes that are introduced in the intersection. Another example, going north to Michigan, you can see the nodes going up and down and left and right of the intersection. And if we zoom in to the southwest side, you can see that error starts to build here with the nodes being kind of leveled down south, so not really centered in the intersection, but laterally they still look decently well, especially along the stop line on the right side. They're lined up pretty well. And a final example of this is at ODOT headquarters in Columbus, Ohio. And this is to kind of show that it doesn't need to be at an intersection, it just needs to be at a place where this data exists and you can communicate it to a vehicle. So zooming in here, you can see that the accuracy is kind of good, and you can also plot things like, unfortunately it's the same color, but the crosswalk up towards the top of the page, you can also plot that. It's just really handy to do some of this simple visualization of some of the data that's being communicated. So some of the data flow that happens with this is that the traffic light through a DSRC radio can send network packets in the form of PCAP data to a receiver, and from that receiver we can pull the data out and pass it through a MATLAB script to take out the desired bytes that we really want to look at. And from there we can pass it through an ASN1 decoder that has a communication protocol to decode these bytes into usable text data that we can pull the reference position or relative positions from that and pass it to our data visualization tool to plot. And so this tool is kind of in the baby phases right now. There's a ton of potential work that would be very interesting to look at. One main potential for it is doing some real-time plotting. So everything I showed you today has been kind of after the fact plotted, but working to get it running real-time in a vehicle to kind of plot your current vehicle position relative to the intersection, as well as other vehicles that are coming through the intersection that can communicate their position. as well as some signal or crosswalk phases would be interesting. And there's also a ton of other data that's communicated through this V2I communication. And some of that includes crosswalks or bike lanes and being able to plot some more of this physical data that's presented. So that's really my tool. So thank you for listening, and here's contact information for me and the contributors of this project. If anyone has questions, I'd be free to take them. Yeah.
What would you need to do to enable real-time visualization?
So for real-time visualization, yes. For real-time visualization, the main objective with that would be able to have a receiver connected to the computer and being able to kind of parse the data through the data flow I showed you right as it's happening, instead of kind of collecting it after the fact and using it. So there'd be a lot of work in trying to sort out what the specific packets being passed across the network that you need, and also the data inside those packets that you need to plot.